As you can see, let me turn on the laser pointer. So as you can see, this is the inch MOSFET designed, right? MOSFET means metal oxide field effect transistor, as you all know. So this is the typical configuration for N-channel enhancement type MOSFET. Okay. So these two sides are mainly N-doped region, and in between we have a sandwiched P-doped region. Okay. And this is your substrate. And this is source substrate, and as you know, this is this source, and for the fate we have one source, one drain, and one gate, right? Using the gate you can basically tune the carrier concentration in this region. Okay, so this is the, and these are the metal contacts, and this is the substrate. Silicon oxide mainly it has been used here. So suppose you pass a current through a source, and is basically coming out from drain. So basically in the, this is the active channel, okay, for this, and using gate you can basically tune the charge density. So one question is given for N-channel type enhancement type MOSFET. Suppose P threshold voltage is 5 volt. So what is the turn on condition for this device? So four options are given over here. So you have to choose the right one. So how to solve this kind of questions? So that I'll discuss. So first you have to understand the IV characteristics for the field effect transistor, right? I hope you guys already know about it, and I am not sure whether it has been discussed in detail or not in the class, but for the sake of remembering, or just to enhance the idea, I will just maybe I'll repeat it if it has been already discussed in your class. So it's better to, like, before solving the questions, it's better to have a look on the basic structure, so that it becomes easier for you to solve the questions, right? So that's why I sometimes I will put stress in the understanding rather than the solving questions. So uh, on that, basically, I believe much. So if the diagram, if the concept and the the understanding is clear to you, then I think you can solve any of the questions. So, similar type of questions were also there in the assignment. So I don't think it won't be difficult for you to solve the questions. So yeah. So as you can see here, the IDS is plotted along the y-axis, and VGS is plotted along the x-axis. So this is the threshold voltage. Okay, this is the cutoff basically threshold point. So this is the typical diode condition, right? So if you provide some certain voltage, after that, basically it's like a turn on condition for the device. It's just like a diode. So see, so here in the cutoff region, basically this is how, with the change of the bias, the bias voltage, this is how the current actually it's increasing in the device, right? With the change of gate voltage, you can see how the drain to source current is getting increased. So this is the cut, basically the cut, as you know, for the standard transistor, rather like NPN transistor or whatever fate, this is the standard configuration. So there are three regions, as you know, the cutoff region where you, even after increasing the voltage between the drain and source, there is literally no current is flowing through the circuit. That's why it is a cutoff condition, right? Zero current is flowing. And ohmic region is like this portion. With a small given applied bias, you are having a current in the circuit. And saturation regions means it's the current is become saturated. The number of charge carrier is becoming saturated over the certain period of, under some certain parameters. Okay. So Vs increases, that is the Vs is greater than Vt. It has to cross the cutoff, unless otherwise it is not possible to change the number of charge carrier. So this is the condition for the diode to turn on. So first you as I mentioned already, this is the cutoff region. So where VGS is basically less than the threshold voltage and ID is zero. Completely, you are not having any kind of source to drain current in the circuit. That's why it's the called cutoff region. And then we have the active region, or let's say the linear ohmic, whatever you are in which terminology you are comfortable, you can just say it. And then this is the condition where like when I mean you have the gate voltage that has been applied, that has to be greater than the threshold voltage, right? And then you have the drain to say source voltage. It's a pretty simple calculation. You can just have a look and do it by yourself also. So then the certain condition, I mean, to fulfill to stay in the active region is drain to source voltage is less than basically the difference between the voltage between gate to source and the threshold voltage in the device, right? Then we quickly come to the saturation region where your VGS has to be, I mean, for both the active and saturation region, your gate to source voltage has to be greater than the threshold voltage. Otherwise, literally, I mean, it will enter into the cutoff region. So that's why the here the current flowing is very important for both this region. So then we have another condition which is source to drain, which is greater than the difference. I mean, this is just a ulta. Okay, then what is there for the active region? It has to be greater than the difference between VGS and V threshold. So now, so as I mentioned, all the terms over here, what does it actually indicate? So this is the gate voltage, this is the drain voltage, VS is the source voltage, VGS gate to source voltage, and VTS drain to source voltage, and VTH is the threshold voltage, ID is the drain current. Basically, drain current means it's drain to source current. Okay, that's it. So it's pretty much clear now what will be the answer. So the condition to turn on the device is VGS is greater than V threshold. So what is the V threshold value is given over here? That's 5 volt, right? So then what option will be the correct? So it's option three, right? It has to be greater than 5 volt. Okay, now let's move on to the next question. So in the next question, so basically you have to answer which of the following statements are correct about the MOSFET. Okay. So first one is it has been given in p-type device current flows due to the electron. The next one is in depletion type of MOSFET channel is already present. So the next one is the pinch off occurs at VDS less than VGS minus V threshold. So now tell me which one is the correct option. So to solve this question, first you must have a proper idea on how this device works. Whether it will be P channel, N channel, enhancement type, depletion type, whatever. First, you need to solve this question. You just need to have a basic idea on this type of MOSFET. Like its working function, what are those majority, minority charge carrier? Those are basically which are responsible for the current flowing in the circuit. Okay. So first, that's why I have written in this thing in step by step. So please go through the slides, or you can also take some notes, and that's why I've made this thing in a bold thing so that it becomes easier for you, also easier to remember sometimes. So this is very important concepts, and at all the stages, I think whatever questions will be there related to this topic, it will help you for sure to solve the questions. So first, the thing is, first one is, of course, okay, just let me turn on the pointer. I don't know why this pointer disappears when I quit and quit the presentation mode. So yeah, just coming back to the topic. So the first one is the P channel MOSFET is a classification of metal oxide semiconductor device, right? Next one is this consists of the in substrate in the middle with a light doping concentration, right? Then it possesses unipolar characteristics. Like it's not like the transistor. I mean the PN junction, or so it is a like it has unipolar characteristics because its operation is dependent on the majority of the charge carrier. So there is no as such minority charge carrier. I mean, it mainly depends on the majority of the charge carrier. What is the majority type of charge carrier? So it pretty much depend on that. So then in this, the majority of the charge carrier are holes. It's P channel MOSFET. It's obvious, right? So because of the two materials utilized in the circuitry. So it's obvious, sir, statement one is correct. Then from this statement, it's clear. Okay, then let's say what happens next. So in any depletion type MOSFET, whether it is an N channel or P channel, the channel is already present and built. So also, I mean, the statement two has to be correct with this. Then let's see. So depletion mode MOSFET is always in on condition without application of gate voltage. Then after applying the voltage, I mean, see, these are I have just mentioned so that you can gather more and more. I mean, as much and information as you get, it will be better for you, right? That's why I have written something extra. So after applying the voltage difference between the source and drain starts flowing through the MOSFET. Okay. So the pinch off occurs in the MOSFET if VGS less than VT. So with this, I have to say key statement three is also correct, right? So as I already mentioned, this is the in-channel depletion. I mean, in the earlier slide, I have shown you the how the working function of the in-channel enhancement type MOSFET. Now this is the in-channel depletion type MOSFET. So you can see this is the diffuse channel in between, and both are like end of here. Okay. So option two is correct, right? Now let's move on to the next thing. So if you are asked to find like the density of states, how we will calculate? So I think in assignments there were, I mean, it was has been calculated. You guys were asked to find out this thing for maybe 1D or 3D. I don't exactly remember, but that's why I had to like tell you for the some different dimensional case as so. See, the concept is similar. I mean, the foundation is same. I mean, you just need to take the Schrodinger equation. If you are given with some potential, then you just plug it in the equation. This then just simply solve it with the boundary with the help of boundary condition. That's it. So that you can also do it for 3D and 1D and 0D as well. So that's why I'm just showing you one of the examples how it. I mean, how it is. I mean, the way it has been. It is generally solved. How people solve this thing when you were asked to calculate the density of states in any of the dimensional space. So let's say we have a model. Okay. So a semiconductor as an infinite quantum well, this two-dimensional with the sides of length L. So you can see inside it, the potential inside this well, the potential is basically zero, and outside the well, the potential is infinite. That's why it's infinite square well, right? Infinite quantum well. So you cannot penetrate in this region. Basically, your wave function will be zero outside this well. So and within this well, it has to be finite. And also the probability of finding the particle over here, it's not exactly zero what you find outside the well. Okay. Now, if you set the potential like as I mentioned, it's zero. So according to the Schrodinger equation, what we get. So just if we put zero, it will become like this. And see, so you just need to break the gradient into all the corresponding two-dimensional. So XY component will come essentially come over here. So then using the separation of variables, the wave function becomes like this. It will be just simply multiplied by, I mean, for the X and for the Y. It's two independent wave function. We are combining using the separation of variable technique. Now, basically, we'll substitute this equation 2 into the equation 1. I mean, over here. Then basically, if we divide this by psi x times psi x y, so we'll uh, end up with having something like this. So this makes the equation valid for all possible x and y terms. Only if terms including this and this are individually equal to the constant. Okay. So you will get something like this. And the solution to the wave function where Vx equals to 0 or sine and the sine and cosine functions, right? So since the wave function equals to 0 at the infinite radius, I mean at x equals to 0 and x equals to plus L, so only the sine function will be valid. So then we'll, if you do that thing, you will get the kx and ky value related to nx and like related to L and with some integers, which is nx and ny, which are plus minus 1, 2, and 3, and so on. So now recalling the from the density of states 3D derivation. So this is the one of the octaves, as you know, one of 1/8 portion of this sphere. So the key space volume of single state of cube in K space is this basically. So this is in K space, so that's why pi by A, pi by B, and pi by C. So it's basically pi cube by V. This is the volume in this K space. So K space volume of the sphere, I mean, this will be pi by 3 pi by pi K cube, right? So yeah, this is the volume of single cube in the K space, and K space volume of the sphere is basically this. So number of field states in sphere, how we'll get this thing? So basically we have to divide the volume of the whole sphere by the single state Kipka volume in K space. And also like we need to multiply with some correction factor for the redundancy in coming count in counting identical states like plus minus nx, plus minus ny, and plus minus nz. So that's why three half are there. And factor is two basically added to for the two spin degeneracy of the electron to for each solution, right? So we'll get something like this thing. Okay, total number of field state, total number of state in the sphere. So for calculating the density of states in a 2D structure or let's say quantum well, we can use a similar approach, right? What we just used for the 3D. So the previous equation then will change to the following. So K space volume basically it will be reduced in a circular form, right? Circular geometry. So it's then the K space. One second. So, for the K-space volume of single state cube in K-space is basically pi by a times pi by b. So it will give you pi square by a square, right? For the square, simply. So the K-space volume of sphere in K-space, I mean, it will be just the area for the circle. That's pi r square, right? So it will be pi k square. Now the number of field state in sphere, it's in, which is v circle divided by v singlet. And again, we have this some other factors which will be multiplied with this, because this too will is basically coming for the fact that electron has a spin degeneracy of 2 plus minus of 2 spins, and this two half factor is coming because of the integer degeneracy like plus minus nx, so and plus minus ny. Then ultimately we are having this total number of states is k square l square over 2 pi, over 2 pi, right? Now this we have already got. Now we'll substitute the value of k with root over 2 me by h square, and that will yield the value in which will be related to the energy. Okay, so we'll, at last we'll have ml square e over h square pi. So the density per unit energy is then obtained using the chain rule. So DND is basically the density of states per unit energy. Then we'll basically do the chain rule and we'll write d and dk times dk d. So that will give you L square m by pi h cut square. So the density of states per unit volume per unit energy is found by dividing by V, volume of the crystal. So it becomes m by pi h cut square. So as stated initially for the electron mass, now it has to be converted to m2. I mean, it will equivalent to M star. I mean the effective mass because of the potential profile. So it will become M star by pi h cut square. So it is the significant that 2D density of state does not depend on the energy. Immediately as the top of the energy gap is reached, there is a significant number of the available state. Right. Now let's move on to the next set of questions. So the occupancy probability P is according to the Fermi-Dirac statistics is you all know it will be 1 over e to the power e minus Cf by kT plus 1, right? Now we were asked to find out the probability of occupancy of a quantum state whose energy is 0.05 electron volt above the Fermi energy. So and also it is given ki you can assume a sample temperature of 450 K and the Boltzmann constant is given over here. So what do we mean by Fermi energy? So it's basically it is the highest occupied quantum state. This system, which consists of fermions at absolute zero temperature, right? So the Fermi energy is a concept in quantum mechanics, usually refers to the energy difference between the highest and lowest occupied single particle state in a quantum system of non or interacting fermions at absolute zero temperature. So Fermi-Dirac statistics is basically describe a distribution of particles over the energy states, right? And system consists of many identical particles that will also obey the Pauli exclusion principle. Now, I'll just simply using this formula, which is already mentioned, ki 1 over e to the power e minus e by kt plus 1, you can solve these questions. So what you can, I mean, if you plug in all the values into the equation, you will get the probabilities 0.2. Okay. If you put all the parameters ka value and the given value, you will get something like this. Then the next question is the if EF is the Fermi energy level and F is the Fermi Dirac distribution function. So what would like what will be the value of E2 minus E1? I mean basically the energy difference over KT by KT. So two energy Fermi distribution function for two different energy it has been given. So simply write down the equation. It is like this. So if you take this, if you put all this value and divide this, so it's will come something like this ln of 19, this factor. So it is very easy to solve. Now let's move to the next set of questions. So for mean free part lambda. So one for mean free path lambda, which statement is right? Which one of the statement? So at constant temperature, lambda increases with increasing pressure. At constant pressure, lambda decreases with increasing pressure. Lambda increases on decreasing the size of the molecule, and lambda increases as the number of molecules increases. So by definition, as we know, the mean free path of the gas molecule is given by this equation. Lambda equals to 1 over root pi root 2 pi d square times n prime, where d is the diameter of the gas molecule and n is the number of the molecules per unit volume of the gas. Okay. So from ideal gas equation, we can write P equals to nRT. Now, where n is the number of the moles, as you know, so Pv equals to n times, I mean, the Avogadro number times R by Na times T. So here Na is the number of molecules in moles. Okay. Simply we can write this, and then here Na by V is basically the number of molecules per unit volume of the gas, and R by N is the Boltzmann constant. So N prime equals to P by KT. So the mean free path of gas molecule is given by this. So it's from here, it's very clear that lambda will be proportional to, like, I mean, inversely proportional to n prime, one root of, I mean, 1 over n prime. So with an increase in the number of molecules per unit volume, the mean free path decreases. So lambda is proportional to 1 over d square. Uh, so option 4 is not true. That means option 4 is not true here. Option 4, it has been written key lambda increases on decreases of the size of molecule. So then with the decrease in the size of the molecules, the mean free path increases. So yes, number 3 is right actually. Number 4 is incorrect because it's showing a proportional relation. So now after replacing n prime by p by kt, we'll get lambda equals to root over 1 over, I mean, if we put this, we'll get lambda equals to kt divided by root over 2 pi d square times speed. So at constant temperature T, the mean free path will decrease on increasing P. So option 1 is not true. And at similarly, that constant pressure, the mean free path will increase on increasing T. So option 4 is also not true. Okay. So now let's move to the next question. So it was asked the mean free path of moving gas particle is directly proportional to the kth power of the diameter of molecule. So here's the value of the k is which one? -2, -1, +1, or +2, +2. So as you already know, I mentioned I mean, what is the mean free path? It's the average speed of molecules in a gas at normal pressure is several hundred meters per second. Yet if somebody across the room from you opens a perfume bottle, you do not detect the order of the several minutes. Order for the separate mist. So the reason for the time delay is that the perfume molecules do not travel directly towards you, but instead travel a zigzag path due to the collision with their air molecules. The average distance traveled by a molecules between collision is called the mean free path. This is the lambda. So the expression we are already familiar by this. So now we'll basically rewrite with something. It will be Vt divided by n by v pi d square times Vt. So it will give me simplifying this, we'll get 1 over n by v times 4 pi r square. So here basically the area of the cross section is pi d square. So the volume of the cylindrical path is given by pi d square times Vt, where t is the time and v is the molecule's velocity. And the number of molecules per unit area is I mean per unit volume is basically n by v. With that, we'll substitute and we can say ki lambda is proportional to 1 over d square. So the k will be your -2. So option 1 is correct. Okay. So now Moore's law is basically related to what? I mean, it's related to the speed of operation of the bipolar device or speed of operation of MOS device or the power rating of the MOS device or the level of integration of MOS device. So it's a very simple question. So Moore's law is an observation that was made in 1965 by Golden Murray, and it states that the number of transistor per square inch on integrated circuits will roughly double every 2 years since the invention of ICs. So Moore's law is related to the level of integration of MOS devices, and Morse predicted that this trend would continue in future also. Moore's law means even more powerful computers for less and less money, right? Now it's one next one is also is a numerical example of relay which is related to n-type silicon devices. So here it was the question is an n-type silicon sample of 10 power minus 3 meter length and 10 power minus 10 meters square cross-sectional area has an impurity concentration of 5 times 10 to the power 20 atom per meter cube. If the mobility of majority charge carrier is 0.125 meters squared per whole second, then the resistance of the sample will be what? So it's 4125 I mean 4 mega ohm, 1 mega ohm, 25 kilo ohm, or 5 kilo. So you just we need to pick up the right answer. So for that, first you need to know what is the conductivity. I mean how it's related with the mobility and the carrier concentration, right? So the conductivity of the silicon sample is given by sigma, which is nothing but NQ mu n, where n is the impurity concentration, mu is the mobility of electrons, q is the electronic charge in coulomb. So the resistance of the silicon sample is given by R equals to rho L by A. So here L is the length of the sample, A is the cross-sectional area of the sample, and rho is the resistivity of the sample. So given, so there are some parameters are already given. So you have to just plug it in the equation, and you just need to calculate the resistance of the sample. That's it. So here n is given, mu n is also given, and q you also know by definition. So see, if you calculate the sigma, it will come to 10. Okay. So then the resistivity is basically the inverse of the conductivity. That is nothing but the point one. And also, so then, I mean, L is a basically is a quantity which basically depends on the system size. Okay, I mean the L length and the area of the cross-sectional area of the sample. So that information we need to calculate the resistance of the sample. So L is 0.001 meter and the cross-sectional area is 10 power minus 10 meter square. So if we plug it in the value in the equation, of like rho L by A will end up of having a resistance is equal to 1 mega ohm. Okay, so hence the resistance of the silicon sample is 1 mega ohm. So therefore the correct answer is option 2. Okay. So now at what temperature, the one question is there. So at what temperature the donor states are completely ionized? Zero room temperature, what I mean, which one is the right answer? So the explanation is that room temperature, the donors have donated their electrons to the conduction band already, right? So the right answer is option B. And second one is the opposite of ionization takes place at what temperature? So it's basically the ground state. So ionization means the excited state, right? We're exciting the electrons into the higher excited state. But if we don't want any ionization, that means that is the ground state. So it's obvious key it is at 0 Kelvin temperature, all the donors and active acceptors are in the lowest energy levels. So at 0 Kelvin, there is no excitement in their energy between the energy levels. So that's why they will stay in the lowest energy possible in the state. So that is called the ground state. So that will be the 0 Kelvin temperature. Okay. So the next questions is In this questions, you were asked to find the breakdown voltage in a reverse bias p-n junction diode. So, so what is the more likely condition to occur due to, I mean, when the reverse bias p-n junction will happen? I mean, breakdown will happen. So, sorry, I put the similar figure. I mean, same figure. I mean, one has to be reverse bias. Sorry, it's just a mistake. So you just need, what you need to do is just connect it the negative. I mean, in forward bias, the P type will be connected to the positive terminal of the battery, and the inside will be connected to the negative terminal. That's it for the forward bias. For reverse bias, so what will happen? Just the vice versa. I mean, P. For the P side, it will be connected to the negative terminal, and the negative side of the battery will be connected to the N type. So, I mean, in reverse bias condition, as you know, the PN junction diode, we attach to the N type, as I already mentioned, with the positive side. So, the possible explanation is in the reverse bias, the ionization of the atoms takes place. And when we applied the voltage, the polarity gets negative and the minority charge carrier accelerated, right? So, when we have the doping concentration, which is very small, so the minority charge carrier start colliding with the other atoms, and the releasing it basically releases the new electrons and produces carrier, which will cause the breakdown. So when we are having the high concentration, a large number of ions in the depletion region creates a very strong magnet electric field, which is basically responsible for the breakdown. So as per this explanation, you can basically see key only option one, which is, I mean, will occur due to the large velocity of the minority charge carrier if the doping concentration is small. And the fourth one is the strong electric field is in the depletion region if the doping concentration is large. So only one and four option are correct. Out of these four options, because the large velocity of minority charge carrier, if the doping concentration is large, is completely wrong statement. And also the third one, which indicates key strong electric field in a depletion region if the doping concentration is small. So that is also a wrong statement. And then I'll move to the next question. So, silicon, it's for the silicon, it's not suitable for the fabrication of light emitting diode. So, what is the reason for this? So, four options are given. So, it's a indirect bandgap semiconductor. This is first one. Second one is the direct bandgap semiconductor. Third one is the wide bandgap semiconductor, and fourth one is the narrow bandgap semiconductor. And fifth one is none of the above is applicable. So what is the right answer? So for this, you need to understand what is the like for silicon, what is the type of band gap? I mean, we get to see and why it cannot be suitable. Okay. So for that, you need to understand the band structure of the silicon in the EK space. Okay. So since silicon is an indirect band gap semiconductor, so electron cannot. So basically, for the direct band gap semiconductor, what happens? So both the K point in the edge of the valence and conduction band, they basically lie in the same K point. So basically there is no change in energy. Energy is also conserved. Also the momentum is also conserved. Okay. So this is happening at the same K point. So the electron can fall directly to the valence band, but must undergo but for this thing where it is slightly shift, you can see the K value is not same for the minimum of the conduction band and the maximum of the valence band. So it electron must undergo a momentum change as well as the change in the energy. Okay, so energy is released as a heat along with the light. So that is why silicon is not suitable for the fabrication of LED. So for this compound semiconductor like gallium arsenide, indium phosphide, they are suitable for the LED purposes because they are the direct bandgap semiconductor. Example for the direct bandgap semiconductor, where in the East K space they both lie in the same K point. That is why there is no loss in terms of, yeah, exactly. So what will be the next question is the temperature dependence of the resistivity of a metal. So, which is the best figure that will describe how the temperature, how the resistance changes, or resistivity of the metal changes with the change of temperature. Okay. So, four graphs are given here. You have to just find out the right one. So, first one basically indicates ki it's increasing with the temperature after a certain point. So, and our second one is basically showing it's decreasing, and third one is basically constant, and fourth one is exponentially it's decreasing with temperature. So for that you need to understand the concept of like what. So what does it understand the concept, right? So what do you mean by resistivity of the system? So the property of conductor that opposes the flow of electric current through them, and independent of the shape and size of the materials, but depends on the nature and the temperature of the materials, is called the resistivity. Okay. So the unit for resistivity is the ohm meter, and the resistivity of material depends on the nature of the and the temperature of the conductor. And the third one is the resistivity of material does not depend on its shape because it's the intrinsic property, and it does not depend on the size and shape. Resistance can depend because it has a length and cross sectional area dependence in its formula. So So you can see how it is basically it depends. Okay. So the property, so the relation between the resistivity, between the, the relation between the resistivity and temperature is given by this expression, rho equals to rho naught times 1 plus alpha times T minus T naught. So where rho is the resistivity at any temperature and alpha is the thermal coefficient of the resistivity, and T is the temperature. Okay. So rho naught is the resistivity at a reference temperature. Generally, we consider it to a reference temperature to 0 degrees centigrade. So the explanation is since the resistivity of the conductor or metal is given by this, I mean, you can see this changing linearly, I mean, according to the expression, and also it has a cutoff, which is the you can say the residue resistivity also. So the resistivity is linearly proportional to the temperature, but in the case of metal, there are free electrons. When the temperature of the metals increases, then the randomness of the free electron will also increase, and the resistivity will quite vary randomly, not in a straight line. So resistance will be increasing with the temperature, but the graph will be quite parabolic. It is seen experimentally, but no mathematical relation is there. So that's the thing. So since there is a constant addition term with t in the right side, that's why the graph will not start from the origin. So option one is correct. So the important points here for the this was for the metal. Okay. So the first option is correct. But for the semiconductor, what happens in semiconductor? As we increase the temperature, the electrons get excited and jump from the valence band into the conduction band, and thereby increases the conductance, resulting in the decrease in the resistivity. So the resistance basically decreases with the increase of temperature. Okay. So these are the things that I wanted to discuss in today's session. So if I hope if you go through all these slides and this YouTube video, what I mean the session what I've recorded. So I hope we will be able to solve all the questions. In that way, basically, I have designed today's session, so it will be quite helpful to all of you guys. So please go through it. And if you have any query, doubts, whatever, you can always contact me via email. Just drop me an email. I'll just get back to you. I mean, I'll try to answer whatever I know based on that. So please reach out and feel free to ask questions. And with this, I would like to end today's session. So I'll meet you next week. Okay, bye.